Hi everyone, I am Tang Renzhi, coming from Guizhou University of China. The topic of my report today is SAD, website fingerprinting difference based on adversarial examples. The main contents I will introduce are background, motivation, detailed introduction of SAD, and evaluation. Now, let me introduce the background. At present, we basically use HTTPS protocol when visiting a website. It encrypts the transmitted data, which makes the transmitted data not stolen by others. However, some other information will still be obtained by others. In this picture, we can directly obtain the IP of both sides of the communication and the website name visited by the user using the packet capture by Wireshark. How do we protect our information? Some people choose to use the anonymous communication system. The currently widely used anonymous communication system term can solve the problems I mentioned above. It mainly uses multiple data encryption and multi-hop proxy to protect information. Unlike the previous HTTPS traffic, Tor has done some protection measures. It has its own data transmission format and will fill each transmission unit to a fixed length during transmission. Therefore, we do not extract the features related to the length of the packet, but only use the direction of the packet. But can this really completely prevent the leakage of user information? As shown in the figure, for Tor, the attacker can also infer the website name visited by the user by collecting Tor traffic between the user and the goal node. This is the website fingerprinting attack. The purpose of this paper is to animate the impact of website fingerprinting attack. Most of the current website fingerprinting attacks use deep learning. The adversarial examples can have an impact on deep learning. So, we summarize the previous defense and combine them with the adversarial examples to have a greater impact on the existing attack models based on deep learning. Now, I will briefly describe our motivation. For the website fingerprinting attack just mentioned, it is regarded as a classification problem. The attack uses deep learning to classify the specified data and obtain the corresponding website name. Our first priority is to mitigate the impact of website fingerprinting attacks. Some researchers have proposed website fingerprinting defense, such as working token, deep fingerprinting defender, website fingerprinting game, and mockingbird. This defense uses the insertion of dummy packets in the naive traffic to achieve the purpose of defense, which means additional bandwidth overhead. Therefore, reducing bandwidth overhead is also more important. Finally, the difference should be applicable in theory. Website fingerprinting game and mockingbird can use global traffic to achieve the purpose of defense, which is likely to be ineffective in practice. Now I will introduce our SAD in detail. We will first introduce its main ideas and explain some more information about it. In this process, we will explain some more implementation details. First of all, this picture shows the general process of SAD. There are several key points in this process: data segmentation, input data to submodel, data joint, and verification of adversarial examples using website fingerprinting attack model. Overall, we generate adversarial examples in segments to simulate the unpredictable traffic pattern in the real scene. For data segmentation, we divide our component traffic into multiple packet segments. Between each segment, we define it as the packet insertion point. If the attacker wants to obtain component traffic, it must also include the packets we inserted, which the attacker cannot detect. As for the adversarial examples of the image, it is required that it cannot be perceived as different from the original image, so people will try to reduce the disturbance as much as possible. In the website fingerprinting defense, the defender does not need to worry about whether the attacker will observe the anomaly after inserting the dummy packet. However, the defender should consider that inserting dummy packets will occupy additional bandwidth overhead. Bandwidth overhead is usually a valuable resource. As a defender, the number of dummy packets inserted should be reduced as much as possible. Here, we describe how to process this segmented data in SAD. The overall model of SAD contains several submodels. We input the segmented data X from front to back into different submodels M according to the length, and the output of these submodels is the adversarial examples Y of this traffic. The number of submodels is a hyperparameter, which is consistent with the type of segment length. We will also make various attempts later. These submodels have no complex structure, only multi-layer, flow-connected networks. But the process is not as simple as it seems. What we need to note is that the value of each dimension output by the neural network is unlikely to be only -1 or 1. Our approach here is to first use Tang to limit the output value to between 1 and -1, and then use Shen to make the non-negative value to 1 and the negative value to -1. But the Shen function is not differentiable, so we need to pay attention to the transmission of the gradient when training the model. It should also be noted that the effective length of the input data of the model is different during training. which needs special treatment here. Within the model, the generated data needs to be connected with the original data in order to generate a complete adversarial examples. Finally, the attacker gets the complete adversarial examples. If he stops collecting traffic at T1, T2, or T3, he will not get the complete traffic to attack. The last step is to input the adversarial examples into the attack model to see the effect of SAD. For generated adversarial examples, it is likely to get a wrong label, even if the label of the source state can be correctly identified. The attack model used here can be any website fingerprinting attack model based on deep learning, and the original data is used to train to the optimal state. The figure shows the training process of SAD. First, SAD outputs the adversarial examples according to the input direction sequence. Then, the adversarial examples are input to the website fingerprinting attack model. Finally, the loss of the model is used as the loss of SAD. Our purpose of optimizer is to make the loss larger. The increase of loss will cause errors in the classification results of website fingerprinting attack model. Next, let's see the evaluation. I will briefly describe several important experiments. First of all, the data used in all experiments are from deep fingerprinting. In closed world, it contains 95 monitored website data, each with 1,000 pieces of data. From Alexa's top 50 sound excluding first 100 sites to build the closed world. It was processed and the number was 40,716. The form of this data is that the packet direction sequence is not a pcap file. One is from the client to the server, and -1 is the opposite. Our evaluation indicators are only simple attack success rates, different success rates, and bandwidth overhead. The specific mean of each letter is on the right. As shown in the figure, we show that multiple website fingerprinting attack models based on deep learning still have stable attack performance under different sequence length spanning. This is to provide a reliable support for the reliability of subsequent experiment results. Next, we use SAD to generate adversarial examples according to different bandwidth cost, and we also did experiments in closed world and open world respectively. We used 3 recent deep learning-based website fingerprinting attack models to test the effectiveness of adversarial examples. From the figure, we can see the excellent performance of SAD. When the bandwidth overhead is only 30%, the success rate has exceeded 19%, and the performance is even better on the open world. In actual scenarios, the attack has been updated all the time, so we simulated this situation. We first use one attack model to train SAD, and use the other two attack models during testing. The results are shown in the figure. That's all. Thanks for your attention. Hi.